Hello everyone, welcome to another video of From Concept to Circuit. In this video, we want to go over some of the fundamentals that we need to know when designing an RF amplifier operating at high frequencies. In the previous videos, we talked about some uh, basic techniques when working with Adam Pluto, which is an SDR giving us an ability to work in high frequencies. But for instance, if we want to expand the range of transmission and receiver in our wireless communication, we need a amplifier operating at high frequencies, right? So we want to know what are the fundamentals in designing an RF amplifier, and then after knowing those, we can go and design our own amplifier. One of the major discussions when we go to RF design is impedance matching. Impedance matching is the matching between the antenna and the receiver, between the impedance of the antenna and the receiver, right? So we want to see with this animation why this is an important thing. One of the things that is making RF design different than low frequency design is because now we are operating at higher frequencies. We want to now take into account the wave behavior of our voltage or our currents. So when they are being transmitted along a transmission line, because of their wave behavior, their voltage oscillates. So let me show you here what I have. So in this animation, we start by propagating a wave from antenna. This is received from antenna, and there is a transmission line until it reaches the receiver. In the receiver, what we have, there is a mismatch here. So some of the wave that is received here is absorbed, but some of it is reflected back, right? And the same thing happens when this reflected wave comes back to the antenna. It gets reflected back because of the impedance mismatch, right? So in this simulation, I've just considered 20 bounces here. One thing is that I consider this transmission line to be a short transmission line, right? So meaning that you can see as the wave is traveling, its amplitude is not being attenuated, which is usually not the case. So when the transmission line is longer, the reflection as it's traveling back to the source gets more attenuated. But let's, for the sake of uh, demonstrating this idea of impedance matching, say the reflected waves do not get attenuated, right? So each time as it hits a wall, it gets reflected back, it bounces back, but with a lower amplitude because um, there is a little matching between the antenna and the receiver, which is determined by this S11 or input return loss here, right? So right now I've set this to minus 6 dB. So 10 by power of minus 6 over 10 is the reflection of the wave, right? But some of it is absorbed. I can change this, but what I want to show here is that let's look at this wave. Let me pause this here, right? So this is our main propagated wave, which is shown in the green, and these are the reflected waves that are bouncing back and forth between the antenna and the receiver, right? What happens is that the combined wave, you can see, has a slightly different phase and also larger amplitude, right? Meaning that it has been distorted when it's being received at the receiver. You can say the same thing at the antenna because if when there is perfect matching here, when the wave is received at the receiver, all of it is absorbed, so now none of it is coming back. But if there is a reflection, the wave comes back here, gets mixed with the main um, wave received at the antenna, and some distortion happens here. So let me resume this. You can see this behavior here at the receiver, right? So this gets worse as I increase S11. You see, because the reflected waves get more in amplitude, they get larger, right? So okay, so what happens here is that due to this distortion at the receiver, what happens is that we are if this wave has a bit information inside it coded, right, with a very short duration, because of this phase mismatch or this amplitude mismatch or other types of distortion, we might lose some of our accuracy at the receiver, right? Because the wave is not exactly the wave received at the antenna. Also, you can say the same thing when the reflected waves come back to the antenna. They come here, they get mixed to the wave, and also because we have an antenna is a passive element, meaning that it doesn't have any direction. It can receive and also transmit at the same time. So when what happens here is that as the reflected waves are combined here, you can actually increase some transmission here at the antenna to the air, and this distortion will be transmitted to the open air. And this is problematic, especially in the modulations when each band, each channel is very, the frequency difference between the channel is very small. So whatever distortion you add here, it can transmit it back to the air and cause issues to the neighbor channels. So that's one of the thing I talked about the distortion. And one other major things here is the power transfer, meaning that when you have an impedance mismatch here, assume that your input has a impedance of 50 ohm, but your receiver has an impedance of 100 ohm. You can say the wave here, if you assume there is a voltage division here, uh, compared to when the input of the receiver is 50 ohm, if it's 100 ohm, definitely the amplitude becomes higher because more of that voltage division comes to the receiver. But at the same time, the power, which is V squared over R, is reducing because you are increasing R. Basically, what we have is that we have a theorem which is the maximum power transfer, which concludes that if you want the maximum power to be transmitted from a source with impedance of Rs, your receiver also needs to have the same impedance if you want to maximize the power transfer. So that's another factor here, right, which is important. These reflections, especially when these are not just limited to wireless communication, they can also be in wireline communications. So especially when you have short channels, when you have these reflections, the distortion that they cause to your signal, they can they can cause bit error and make your the signal you see at the receiver um, more distorted. So I guess this is one of the things I wanted to show in this video, why impedance matching becomes important when we are designing an RF circuit. If I resume this and uh, reduce reduce S11 to, let's say, minus 24, you can see because the reflected waves now are much smaller, the green wave, which is the actual wave that is received by the antenna, is almost the same as what is received at the receiver, right? Usually in RF design, we try to make the S11 to be minus 10 dB, meaning that only 10% of the wave is reflected back. But sometimes we need to go for a smaller S11 to minus 20, or even in some cases when we are designing a very wide band amplifier, we may be still be okay with an S11 of minus 8. So this is one of the fundamentals when we look at an RF frequency. when we look at designing an RF amplifier in high frequencies. So now let's go to other uh, uh, fundamentals. Okay, now let's continue in exploring the fundamentals. We are trying to explore these fundamentals to because need to have a solid background when we want to go in the future with those to make our own RF amplifier. First, we need to know what is important, what are the things that are needed to be considered. Then, based on those, we try design our own RF amplifier that we can use in our projects with software-defined radio, with Adam Pluto to expand the transmission range and etc. So one thing to note here is that designing the amplifier when we are in integrated circuits, because the integrated circuits are in very small areas, the distance between each block, each amplifier or transistors to each other are very short. So um, we are talking about micrometers range. So for the signal to behave as a wave, to be considered more like a wave, its wavelength should be comparable to the length of transmission. Meaning that when we are talking in uh, design of integrated circuits, we are not usually worried in the transmission line effect if the signal is not very high frequency. Usually maybe after 20 gigahertz or even more, we need to consider some of the transmission line effects. But still, whatever we do in the integrated circuit, when we want to interface to the output or the input signal needs to come to the integrated circuit, this interface matters because now it's not very easy to communicate with the outside world. Now we need to have the pads for the IC that are usually larger in size, which add some parasitics or other effects come into picture, which require us to be more careful when we are interfacing with outside world. But that's another discussion. We just want for now focus on discrete amplifiers, meaning that if we want to make an amplifier at home, what are the requirements? Basically we can have a PCB, we can design everything on the PCB, we can buy a transistor from the market that can work at higher frequencies. So we just need to combine and connect these things together appropriately so the amplifier works properly. Now, because of the traces being longer, we need to consider the transmission line effect because now we need our signals are behaving like a wave, as the video I showed earlier. Uh, so then the transmission lines become critical. Our transmission lines, usually they have some properties called yeah, characteristic impedance, and we need to design the characteristic impedance with the requirements of our design, for instance, 50 ohm. So that as the signal is traveling through this transmission line, it doesn't face too much distortion or reflection. There are different ways to create a transmission line. In a PCB, for instance, we can use a microstrip line, which is basically we have the dielectric, this is the track line, and then we put a ground plane underneath. There are other types, a strip line, coplanar, waveguide. So this is one of the other ones, coplanar waveguide with ground, which is basically we have this ground plane. This is our signal, but also we have two ground planes beside our signal. Usually, there are some equations you can use to design these transmission lines, but we need to rely on some simulations to be very accurate. There are softwares to do that. That they do like electromagnetic simulations for us. We can use HFSS or simpler version, Advanced Design System (ADS) by Keysight. That's a very useful tool. But for this design, I found that I can use actually ANSYS electronic desktop, one student version of it, and use that, which is very useful because it with that license I can use HFSS and other circuit simulations to not only accurately design the transmission line, but also simulate the rest of the circuitry. That's another discussion that we want to explore in the future videos when we want to actually go to design of the amplifier. First, we design the transmission line simulated inside that electronic desktop by ANSYS. Then we put everything in the circuit simulation and design the whole thing. Um, and be sure to subscribe to not miss the future videos. Okay, continuing on, I just want to mention some things about this, show what a common RF amplifier and what are the considerations we need to take care of. For instance, you can buy this type of amplifiers in Amazon. They say it's a 5 megahertz to 6 gigahertz 20 dB amplifier, uh, and they are very cheap. You just need to apply a 5-volt supply to them, and then they provide 20 dB gain, which is not a very bad gain. But then how this discrete amplifier is made? So this is the circuit, the RF amplifier when the cap is removed. There are a few interesting things here. One is inside there is a IC called SBB5089Z. There are two capacitors and I believe two inductors uh, and two capacitors going to the supply. So this capacitor and this capacitor are uh, the capacitors for DC block from the input and output, and this is the inductance that provides the supply at the drain of this amplifier through the supply. I actually, you can find this integrated circuit in market. It's by Corvo SBB5089Z. It's a 50 megahertz to 6 gigahertz cascadable amplifier. This is a very useful IC because we can use it, and using that we can make our own amplifiers based on the design requirements we have. So just want to show you it it says about the frequency range. It talks about the flatness of gain P1 dB compression point uh, of the amplifier and the supply. You can also find other interesting things in the datasheet. For instance, there is one interesting thing inside the datasheet that talks about the evaluation board. This is the evaluation board that they suggest, which I think if you compare, it's very close to this inside the amplifier that we bought from Amazon. I just want to talk about the different components of this evaluation board and show you what are the things needed to be considered and what are each components doing. So when we go want to make our own amplifier, we do the same. So one thing before moving to that was, although inside the datasheet there isn't so much information available about what is inside, but I think I can say the inside probably might be something similar to this IC ERA5 plus, which is basically two bipolar transistors that are biased inside the package before going out. The reason I'm bringing this up is I just want to show you how a wideband amplifier can be made, one of the techniques. So for an amplifier, what we need is we need the transistors, and here they use two transistors in series with each other. We call this Darlington pair because it gives us more current gain when we put them with this configuration. One other thing is that how we can generate the bias voltage for the base of this transistor. We can use a voltage divider through this resistor to from the drain voltage generate the base voltage. Sorry, I think this is a collector here in BJT, not drain. But anyway, it can be a MOSFET, and we call this drain. But one other interesting thing I want to discuss here is how we can generate a wide band matching now that we have our biasing, we have our current gain. One of the way is that because at the input, when we look at the input of this amplifier, we need to see 50 ohm across all the frequencies. That's why they put everything inside the integrated circuit. So they could, the parasitics of these resistors are much less if compared to when they wanted to add this outside of IC, right? That is why when they put these resistors inside IC, because of low parasitics, they can offer the amplifier from 50 megahertz to 6 gigahertz, right? And also they create the matching with this because you can just simply say, I create the matching by having explicit resistor, 50 ohm resistor, or uh, make the equivalent when I look at the base to be 50 ohm. So across all the frequency range, because it's a resistor, its impedance does not change. I just look at the 50 ohm, right? But you can also use the same bias feedback resistor to create that 50 ohm matching, because now Miller effect comes into the picture. And what you can do is that this resistor, because if you want to see its effect at the base, when you look at the base, its effect is divided by the gain of the circuit. So essentially, you will see this RF divided by your gain. You can design this resistor to be large to reduce the noise of this amplifier while also maintaining the input matching. In the future video, we discuss about different types of uh, wideband amplifiers that we can make for integrated circuits, which this becomes more clear. But for now, I just wanted to show how this transistor is probably made. Now back to the evaluation board. Now I know that I have, when I look at SBB 5089Z, I will see 50 ohm across the frequency band of 50 megahertz to 6 gigahertz. I just need to make sure that I design my transmission line in such a way that its characteristic impedance is also 50 megahertz, 50 ohm. So uh, when uh, when my amplifier in the PCB is here and it's transmitted to this SMA connector, its impedance does not change. So I don't see a reflection. The same is for the output here. So I need to be sure that my transmission lines, which in this case are coplanar waveguides with ground plane underneath, are designed with characteristic impedance of 50 ohm. In the future video, we'll see how we can design and simulate such transmission lines. Also, these are the capacitors that are used to block the DC coming from the input to the amplifier or coming from the output to the amplifier. And their value needs to be designed for the frequency of our interest, because essentially what they do is that because we have a capacitor, and you can assume that here you see a 50 ohm resistance, you will see a high pass response here. And if your amplifier you want to work at 50 megahertz, you need your high pass filter needs to be designed in such a way that it's at least uh, one decade before that 50 megahertz, let's say 5 megahertz, so you are sure if you have 50 megahertz at your input, most of it is going through the circuit. So that's about the design of these capacitors. And one other thing for providing the bias. Usually for providing the bias for RF amplifiers, we want to provide the bias in such a way that it doesn't add any unnecessary load to the circuit at high frequencies. And what is high impedance at high frequencies? It's an inductor. It's very low impedance at low frequencies, so it can easily pass high DC currents. But at high frequency, you can assume it to be high. You can assume it to be a high impedance or a floating component, right? That's why we use an inductor when we want to provide the supply voltage here, because it not only at high frequencies uh, load the output, but also it acts as a filter, filtering the whatever high frequency noise our supply has to the output of our amplifier. Another filtering effect and also another way to stabilize the supply by having some capacitor, so in very they can provide the current when the rate of the change or the current is high, is adding capacitors. Usually when we add more capacitors, it helps us because it reduces the noise, and it also acts as a reservoir for charge in case that we need it, right? In case that we need a very high current in a short amount of time, we can use the charge stored in the capacitor. But the challenge is that as the capacitor sizes increase, because any component as their size increase, the the contacts inside it, their sizes increase, the wirings inside them increase, and etc. Their parasitics increase, right? So ideally, you want a very high capacitor here, but when in components you increase the capacitance, all the parasitic effects come into the picture. You see also large resistances from the plate of the capacitor to the outside world or to the ground, that reduces the quality factor or reduces the ability of the capacitance at higher frequencies. That's why usually in the design, we try to use multiple capacitors at different uh, values. We provide a high value capacitor, and we know that this high value capacitor is probably is not good at high frequencies. So we add another lower value one for middle frequencies and a very small one for very high frequencies, because this, let's say this CB of 68 pico, because it's very small, its parasitics are small, so at very high frequencies, this capacitor will act more like a capacitor compared to the larger ones, right? So these are the things that I thought to discuss before moving on to the actual design, uh, simulating the design in the future videos. And please give me your feedback uh, if you need clarification in any of these, or you want something we discuss in design of these amplifiers. So now that we know the basics, we know that one of the things that we need to take care of is the impedance matching. When we want to design the circuit, first we want to have the ability to simulate this. What we can do is that usually the IC providers provide us with S parameter file of their amplifiers. So we can, using those S parameter files, we know what is the input return loss of the amplifier, which is called S11, and based on that design the whole circuit. We can know S21 of the amplifier, which basically is the relationship of output to the input, or in other words, the gain of the amplifier, or S22, which is the matching to the output, right? So what we need to do is usually when we work at higher frequencies and we want to design a discrete amplifier, we need to, whatever components we use, we need to find their S parameter file from their providers, then use those S parameter files, add them to our simulations, and using those, find the overall S parameter of the amplifier. So we need to find, if we use a capacitor in the main chain, we need to find its S parameter file. Also at the output, we need to know the S parameter file. We need to know the S parameters of the amplifier, and all these transmission lines, we need their S parameter. But the way for to find the S parameter of the transmission line is using using a simulator that can extract the information of the transmission line by uh, solving all the Maxwell equations for this transmission line via electromagnetic simulations. We'll try to one by one go over this in the future videos. That's it for this video. I hope you enjoyed it. Please subscribe, and um, please let anyone that you think that can benefit from these materials, please let them know, so our channel base grows. And also give me feedback through the comments. I really appreciate it. And thank you.